In this video, we're going to look at the design of a single-bit storage element called a flip-flop. In a previous video, we saw another storage element called a latch. It turns out that latches have a significant deficiency that flip-flops correct. First, we'll review the operation of a latch. A latch has two inputs, a data input D and a write enable EN, and an output Q. When EN is 0, the latch is in hold mode, and it holds the value of the output even as we change the value of the input. When we take EN high, the input writes to the output, we're in write mode, and the output follows the value of the input. When we take EN low again, the latch holds the new value. Here's the problem with a latch. Suppose that we wanted to design a counter that consisted of a latch that holds the current value of the count and an adder that takes the current value of the count and adds 1 to it. What we'd like to have happen is every time the enable to the latch goes high, that the count increments by 1. The problem, however, is that the latch goes transparent when the enable signal is 1, meaning that the output Q follows the value of D. In other words, while the enable signal is 1, the latch is behaving like a wire, so that instead of a counter, what we actually get is an oscillator that just keeps incrementing as fast as the adder can add 1 to the current value of the count. In theory, we might be able to limit how long we keep the enable signal high such that it's only high as long as the time it takes to add 1, but in practice we'd never be able to get this to work. Rather than using a latch that keeps writing as long as the enable signal is high, we'd prefer to have a storage component that just writes once when the enable is taken high. That's what a flip-flop does. In a flip-flop, we've replaced the enable input of the latch with a clock, and that clock is edge triggered such that it only writes on the rising edge of the clock. Unlike a latch that goes transparent when the enable is high, the clock only writes on the rising edge, so we get the behavior of the counter that we're looking for. This simulation shows the operation of a flip-flop. Initially the clock is low, and if we change the value of the data input D, the output holds its value. When we take the clock from a 0 to a 1, the data output gets the new value, but unlike a latch, we can change the value of the data input D, and the output value doesn't change. We take the clock low again, and again the output holds its value, but on the next rising edge of the clock, we write the new value to the output. So how does a flip-flop work, and how can I build one? To motivate what's going on, let's take a look at an example where I've just gone grocery shopping and I want to get the groceries into the house, but inside the house I have a dog that's always trying to escape. In this example, the latch is like the door. So what happens is I open the door and I start carrying the groceries in, but because I have an armful of groceries and the dog is more nimble than I am, it gets out. Now suppose that instead of going directly into the house, I'm going to come into, let's say, the utility room first, and then enter the house, so I have a system with 2 doors or 2 latches. So I can do this in 2 phases. So I'll open the first door from the outside, let's call this the flip stage, and I can carry the groceries into the corner of the utility room. And then I'll go to the flop stage, where I close the outside door and open the inside door. Now the dog can run into the utility room, and I can slip down around the corner and into the house without the dog escaping. So the trick to keeping the dog inside was building a system that had 2 doors. So on either side of a pulse, we used 2 phases, a flip stage where we opened the outside door, and then going into a flop stage where we closed the outside door but opened the inside door. And rather than using doors, here we're going to use latches. So we'll use a pair of latches. The first is enabled and goes into write mode when the clock is low, which is the flip stage. And the second is enabled when the clock is high, which is the flop stage. So one of the latches is in write mode while the other is in hold mode, but the pair never goes transparent. This simulation shows the design and operation of a D flip-flop made from two latches. Overall, the system has two inputs, D and clock, and an output Q. The Q output of the first latch is connected to the data input of the second latch. The write enable of the first latch goes through an inverter, so it sees the value of clock bar as write enable, while the second latch gets the value of clock directly. Initially, clock is low, so the first latch is in write mode since it has a 1 on its write enable, while the second latch is in hold mode. As we change the value of the data input, since the first latch is in write mode, we see that the value internal to the flip-flop at the midpoint between the two latches follows changes in D, but the output Q doesn't change since the second latch is in hold mode. Now when we take the clock high, the first latch goes into hold mode while the second latch goes into write mode, so the value at the midpoint shows up at the output. While the clock input is high now, though, we can change the value of the data input, and the midpoint value doesn't change because the first latch is in hold mode. So of course the value of Q doesn't change. Now when we take the clock low again, we see that the value at the midpoint changes, but the second latch was in hold mode doesn't. And on the next rising edge of the clock, the value from the midpoint gets transferred from the output since the second latch goes into write mode, but the first latch goes into hold mode. So looking at the waveforms, we can compare what happens with the flip-flop as compared to what would happen with the latch. The biggest difference is that while the clock value is high, even though we're changing the value of the data input, the value of the output Q doesn't change, whereas in the latch, the value of the output Q would follow the changes in the input D. And also the important thing is that the changes to the output Q appear to happen right at the rising edge of the clock, even though we now know that it takes the full pulse to go through the two phases, flip and flop. Here's a simulation of the flip-flop showing the internals of the latches with their inverters and switches. This makes it really clear which parts of the circuit are connected and which parts of the circuit are not in either phase of the clock. So initially when the clock input is 0, clearly the first latch is in write mode because you can see the connections all the way from the D input to the midpoint internal to the latch, and the feedback loop is open. While the second latch is in hold mode, the feedback loop is connected, but the switch at the beginning has it decoupled from the first latch. So as we change the data input D, we see that the first latch is transparent and that the midpoint changes with the input D. But now, when we change the clock from a 0 to 1, the first latch clearly goes into hold mode while the second latch is in write mode, and the value at the midpoint shows up at the output Q. Now, since the first latch is in hold mode, we can change the value of the data input D, and the value at the midpoint doesn't change because clearly that data input is decoupled from the rest of the circuit.